And what I want you to do was to do the derivation of the relative velocity relationship. That it's something new I've learned from ChatGPT apparently. So during the October 11th session, it came up. I was pretending I'm having trouble with algebra. So I was asking ChatGPT, how do I do this? And when I first saw the mention of the formula, I actually didn't believe it was correct. So, this is where I was working through this and pretending, oh, I'm having trouble with the algebra. And then ChatGPT told me this. For elastic collisions, there's a useful relative velocity relationship. This. And, when you first look at it, this just looks way too simple. You think, that can't possibly be right. And apparently it's right. And I did find the derivation of this relationship, not in our textbook. Our textbook doesn't seem to cover it, but it's definitely in the textbook that we used to use, Giancoli. And it's also in the textbook that I learned my own lower division physics out of, Young and Friedman. So you could say that I should have known that such a relationship existed, and either I skipped over the textbook section, or if I read it, I just forgot it. So let me take some time today now to actually derive it and just to talk a little bit about how I think you should use it in your problem solving. And actually, I might redo some of the homework help videos in future semesters using this relationship, because it does make the algebra much simpler. So let me quickly go through the derivation, because once you know what you're doing, as I do now, the derivation is actually pretty simple. So let me write down the title of what I'm driving. Relative velocity relationship for elastic collisions. And I don't know if there's a standard name for it. This is the name that ChatGPT was using, and since I learned it from ChatGPT, let me use ChatGPT's word for it. And I guess I could refer to the derivation that's done in Giancoli or Young and Friedman textbook, but then there's a copyright implication. So let me do an independent derivation here so that I can share this without worrying about someone else's copyright. So we are considering a very general situation of an elastic collision. You imagine 1D elastic collision. You imagine having a mass m1 coming in with some initial speed v1 and striking m2, which has some initial velocity v2. And I've drawn everything to the right, but these could be going to left. Then you would just let the velocity be negative. So this is the before picture. And after the collision, there's a final picture of, so after the collision, M1 will be moving in some way. Let's say it's still going the same direction. And let me call this V1 prime. And M2 is doing its own thing, moving at some speed. Let me call this V2 prime. And that's the post-collision picture of the setup. So when you are analyzing this setup, you can use conservation of momentum and energy, like conservation of momentum, like any collision that you have seen. So let me write that down. That says the initial momentum is equal to the final momentum when you add up everything. Rewriting this schematic relationship in a more concrete terms, in terms of the variables we have, what this is the sum of the momenta, m1 times v1 plus m2 times v2. Again, this is completely general. If the particles happen to be moving to the left, then you just let v1 and v2 be negative. Completely general. You say that's equal to their total momenta after the collision. m1 times v1 prime plus m2 times v2 prime. I'm using prime just so the writing is not so colored down in the subscript area. So conservation of momentum. Now, because it's an elastic collision, we can also say conservation of energy. More specifically, conservation of kinetic energy. That's really what elastic means. If there's like potential energy involved, we usually wouldn't call it elastic collision. But even though total energy might be conserved. So with the conservation of kinetic energy, what we should say is the total initial kinetic energy is equal to the total final kinetic energy, or making it more concrete with the expressions we have. That means 1 half m1 v1 squared plus 1 half m2 v2 squared is equal to 1 half m1 v1 prime squared plus 1 half m2 v2 prime squared. Now, so before I was using these equations directly, trying to solve for some things that are being asked for. Today, my goal is different. My goal is to derive this relationship here. And actually knowing the form that we are getting to, it's helpful because it becomes a hint to which way we should go. So I'm noticing that it doesn't have masses. So whatever derivation steps I'm going through must somehow cancel out masses. And I noticed that this is actually the surprising and useful thing about it. This is linear in order. That's what made me initially think that that couldn't possibly be right, because we have this quadratic thing in energy expression. So you know, that's what was making math difficult. And so in the derivation step, somehow we must be getting rid of these exponents. And what that means is there might be some factoring involved as we are going through the derivation steps. So let me go through some steps that are motivated by these features of the expression that we are getting to. So the number one thing that's motivated by the fact that they don't have masses is I'm going to try to collect them in like terms, in terms of masses, so that I can factor out the mass and see how there might be some cancellation. So I'll collect all the m1 terms on the left-hand side and all the m2 terms on the right-hand side. Let me do that for momentum. Then I get m1 v1. I'm moving over m1 v1 prime, so minus m1 v1 prime. And I'm moving over m2 v2 to the right-hand side to get m2 v2 prime minus m2 v2. All right. And let me do the same thing with the kinetic energy expression. I'm going to collect all the m1 terms on the left-hand side, all the m2 terms on the right-hand side. So 1 half m1 v1 squared minus 1 half m1 v1 prime squared, having moved that over. And on the right-hand side, I have 1 half m2 v2 prime squared, and from having moved this over, minus 1 half m2 v2 squared. Let's do some simplifications. So I can cancel out some simple numerical factors, like this 1 half. I can just imagine multiplying through the whole thing by times 2. That gets rid of all these factors of 1 half. Don't have to deal with them. And I guess I should factor out the masses so that I can see best how it might cancel out. So let me do that factoring. Let me organize my expressions a little bit so that I have a little more space. All right, so now I have enough space down here. Let me write down the simplified expression. So from this equation 1, I'm going to have this 1 prime. With the m1 being factored out, I have n1 times v1 minus v1 prime is equal to m2 times v2 minus v2 prime minus v2. And from my equation 2, factoring out m1 and m2 again, I have 2 prime, which will be m1 times v1 minus v1 squared minus v1 prime squared is equal to m2 times v2 prime squared minus v2. Now, as you stare at this, I hope you remember some useful factoring relationship that you might have learned in college algebra. If you have expression like a squared minus b squared, this can be factored into this form, a minus b times a plus b, which means this can be factored into this form. So this being a, this being b, it will be v1 minus v1 prime times v1 plus v1 prime. And this can be factored in a similar way, v2 prime minus v2 times v2 prime plus v2. Hopefully that sounds familiar. Now, if it doesn't sound familiar, then you can verify. Take the expression here, expand it out. You will see cross terms cancel, and you'll be left with a squared minus b squared. So I'm going to make use of that because this is what I'm noticing. I'm noticing that this term here that I'll get out of factoring this is going to be equal to this, so I can cancel it. This I get out of factoring this will be equal to this, so I can cancel it. So if I write down something that looks like 2 prime as an equation divided by 1 prime as an equation, then this is what I get. I'm just going to write down the factor diversion. So it will be m1 times v1 minus v1 prime, v1 plus v1 prime, divided by the left-hand side of the 1 prime equation, m1 times v1 minus v1 prime is equal to the right-hand sides, m2 times v2 prime minus v2 times v2 prime plus v2, divided by the right-hand sides of the other equation, m2 times v2 prime minus v2. So a lot of things cancel out. I get the masses canceling out. That's what I was looking for, so that my final expression won't have masses. And this is the part that makes my final resulting equation linear in order. This one, linear dependence on velocities, cancels out from the factored expression. So you are just left with this final expression, which is wonderfully simple. That v1 plus v1 prime, that is the sum of the velocities of the object 1 before and after, minding the directions. If it's somehow moving to left, then you make it negative. That's equal to v2 plus v2 prime. Now, it's in a slightly different form from how ChatGPT had it, but I think I actually like this form better. I think I can remember this a lot better. Sum of velocities of one object is equal to sum of velocities of the other object. And its usefulness in problem solving is, imagine you are trying to work out velocities of some objects after an elastic collision. So doing it in a traditional way, you might use these two equations. And with this equation being derived out of those two, this is what it means. Between these three equations, conservation of momentum, conservation of energy, and finally this expression that we just derived, v1 plus v1 prime is equal to v2 plus v2 prime. Between these three equations, you have two independent equations. So if you have two unknowns, you can solve for them by picking any two out of these three equations. And before, when I was trying to solve those questions using conservation of energy, I had to deal with these square terms that always made my algebra complicated. But if I now instead of the conservation of energy expression, if I pick conservation of momentum expression and this relative velocity expression, then between those two equations, they contain all the information that was in the original set of equations. So without explicitly using conservation of kinetic energy, using this in conjunction with the conservation of momentum already puts in the information that's coming from conservation of kinetic energy. And in doing this algebra, I never have to square anything. Everything remains linear. I feel a lot more confident working this system of two equations than having to deal with the squaring and whatnot. And if you are a skeptical person like me, you might look at it and think, that sounds too good to be true. What's the catch? I will tell you what the catch is, because there is a catch. And in fact, I did something that your math instructors would disapprove of. This cancellation that I did here, it's improper. I shouldn't have done it, because there's a possibility that this is 0, and I'm not allowed to divide by 0. So, or, flip it around. By doing this cancellation, I'm implicitly saying that this is true, or to be more precise, the mathematical operation I did is invalid unless this is true. So this must be true for me to not have done something naughty. So this v1 minus v1 prime must not be 0, which means we must have v1 not equal to v1 prime. And v2 prime minus v2 must not be equal to 0, which means v2 prime must not be equal to v2. Now, consider looking at this. What kind of solution do you have when v1 is equal to v1 prime? And what kind of solution do you have when v2 prime is equal to v2? It's the trivial solution. It's the solution where nothing happened, where two things are colliding and they just pass each other. So initial velocity of an object is equal to its own final velocity. Initial velocity of another object is equal to its own final velocity because they didn't collide, they just passed through each other. So in using this relative velocity equation, you are losing some information. You are throwing out this possible solution that's a mathematically valid solution that you could have had. But it's the exact solution you don't really want physically anyway. It's the trivial solution where nothing happened. So yeah, there's a catch, but that catch is the kind of catch that we are actually happy with, because it means we don't have to deal with that redundant extraneous solution that we were going to throw away anyway. So that step is done automatically in this derivation step. So this is the relative velocity relationship. Again, many standard textbooks do actually derive it. Giancoli and Young and Friedman, those are the two I checked. So that does it. OpenStax for some reason doesn't do it. But I do think this is a useful formula to have memorized and possibly use it when you see elastic collision problem that could be difficult. And I might actually redo a lot of my lectures on elastic collision using this relationship, because I gotta tell you, I've been doing physics for over 20 years, and this is something new I've learned that I should have learned 20 years ago. So it's all right. Thank you, and I'll see you in the next lecture. Bye.